How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And our special business today is more on sound waves, and more deliberately on these two matters: frequency and pitch. When we speak of a sound, we ascribe to it a certain pitch: A, B, C, D, E, G. A, for example. If I strike A, let me do that. Here I have a bar, which I'm going to strike. That bar has a certain mechanical motion so fast, we call it the frequency. It gives rise acoustically in my ear to my brain a property called the pitch. For example, I struck a bar which vibrates 440 vibrations per second, and we call that A. We call that A. If I struck a tuning fork, let me find one here. I will strike a tuning fork quite like so. That is vibrating 256 vibrations per second, and we call that middle C. So, the mechanical behavior of a vibrating system, we call its frequency, and what emerges acoustically, we call the pitch. Let me illustrate. Here is a metal... Oh, and by the way, it needs to be remembered, and very clearly, that in order to have a sound, we must have a vibrating system. And for sound energy to be propagated, there must be a medium for it. Because remember, sound waves are compressional waves, and there has to be something to compress. So here is a piece of steel plate. I'm going to flex it. Listen. It has a certain frequency. It's giving rise to certain pressure pulses that advance upon the microphone and upon my ear. I spoke of pressure pulses. I want you all to try this adventure. It is quite remarkable. Hold your arm in this matter and do some talking firmly on the arm. I say that I feel the changes in pressure on my arm, which emerge from the pressure pulses coming out here, a result of the behavior of my lungs, and the voice that I have is governed by the frequency of my vocal cords, how my mouth is shaped, the position of my lips, where my tongue is, and whether I have teeth or not. A very important thing. Here is another sheet of stuff, a bigger sheet, bigger, more inertia, likely to have a lower pitch. Yes, it does. And here is a bigger sheet of the steel, the like of which I had in the first place. Bigger, more inertia, lower pitch. Lower pitch. Let me speak more of that frequency and pitch business. Here I have some metal discs, which are notched. This one, I hope you see, has 4 notches. That one, 8 notches. That one, 16 notches. And this one, 32 notches. Now, if I put this shaft in a rotating motor and spun it, and held a card or a flexible piece of steel against this one, I would get for each revolution 4 pulses to the ear. This one would give me 8 pulses, this 16 and this 32. Hence, although they have the same angular velocity, they have different frequencies of pulses reaching my ear, and therefore different pitches. Let me show you that here. I have a disc with some holes in it. And I call your attention very especially to the following. The outermost row of holes has the mostest holes. The inner, the next inner, less holes, less holes, less holes still. All these 4 rows have their holes symmetrically separated. The innermost row of holes has its holes unsymmetric. So, if you give me your attention, I am going to try to show you the difference between music and noise. Now, I'm going to have some difficulty with that because for some, boogie-woogie is music, but for some of us, it is not music. Watch me. I'm going to rotate this at a certain speed and drive a stream of air through successive rows of holes. Watch this now. Watch this. Watch. Now I'm going to go faster. Now I'm going to go faster still on the outermost row of holes. Watch it. So you see, the higher the frequency, the higher the pitch. Now all of these emitted pressure pulses were pleasant sort of to the ear. We call that music. Not only that, but the frequencies can be written in a simple mathematical way. Now I'm going to proceed from the outermost to the very innermost, and there the lack of symmetry will tell us something about the difference between sound, music and noise. Now, watch it. Watch now. Watch. I don't think we could classify that innermost one as music. More on vibration frequency. Notice, a meter stick. A meter stick, I fix it to the table so, with such a length hanging over. Very high frequency, very high pitch. Lower pitch. Lower pitch. Lower pitch. Lower pitch still. So I have tried to connect for you pitch and frequency. Consider this, which Galileo observed. Here is a silver coin, a $50. It is milled on the edge. I hope you know why it is milled on the edge. I'm going to run my thumbnail over it, doing exactly what Galileo did in the 16th century. Listen. Now I'm going to take a silver dollar, and I think we'll have a different pitch. Why? The milling is at a different rate, and the inertia of this is of a different sort. Listen. Let me take a quarter, a dime. Remember, something is vibrating. Or just tearing a piece of cloth. Here is a piece of cloth. Listen. Vibrating system. Here is something else that I'm going to tear. Different pitch. Or consider a board which I rasp with a large file. Listen. Certain pitch. Finer file. Higher pitch. Very clearly that. Very clearly. Or take a deck of cards. Listen. Listen. Or a larger deck. Larger inertia, more mass, lower pitch. Now, more of the same. You remember the flexible steel plate, the flexible brass plate. Larger. Now, question. Here is a plate. Listen carefully. Listen. 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 I hear nothing. Somebody says, it ain't vibrating, Professor. Oh, it is vibrating, but at such a very low frequency that it is below the audibility of the human ear, which leads me to remark that the human ear range goes from about 16 vibrations per second to about 16,000. Some say 20 to 20,000. Now, the vibration frequency of this lead plate was so very low. Now, consider, again, the tuning fork business. Did I not say that if I strike a fork, it has a certain frequency, therefore it emits a certain pitch? Later in this series, I will show you a wonderful thing. Here is that bar that I have already struck and made sing. And you'll notice that bar is fixed here and fixed there. These are positions of rest in the bar, and they are called nodes. And the bar is really doing something like that, which I will show you in another lesson. Now, how about a tuning fork? Well, a tuning fork is a bar. There is the bar. And the tuning fork was bent up so that these two nodes are very close together, and a handle was put on. And thus is the mechanism of a vibrating bar. More on the same, but of a different complexion. An enchanting little business that is essentially a toy, but which can be made to emit music. Here is a prismatic rod, rectangular rod, which is notched. And you see that if I run this the stick across the notches, it goes into that hole and up, into that hole and up. Here is a little propeller on the end. Watch the behavior of the propeller. The propeller has a frequency governed by the frequency of the notches on the stick. Mark you too, this rotated this way when I stroked it here. Now watch it. Aha, aha. And in another lesson, I will talk about compounded harmonic motions which give rise to some beautiful things. So, let us sum it up. An orchestra tunes up. The maestro comes in and starts, but before he starts, I ask, by what instrument does the orchestra tune itself? Everybody thinks it is the piano, but that is not right. Now, why is that not right? Because the piano has metal strings, and metal strings change in length, and therefore in tension, and therefore in frequency, and therefore in pitch. So there is one musical instrument by which the orchestra tunes. I leave you now with this question. The auditorium gets hot, the musicians get hot, the instruments get hot, and the instruments get out of tune. Question, what happens to the wind instruments, and what happens to the stringed instruments? And we shall see this on another program, because all that emerges from vibrating bodies is sound of some sort, and some wonderful to hear. And I shall be with you another day. How do you do, ladies and gentlemen, and boys and girls, and teachers? I'm Julius Sumner Miller, and physics is my business. And my program today has to do especially with this, how to produce electricity. And I call to your attention the quotation marks in the word for the word produce. We do not really produce electricity. The electric stuff is always there in abundance, always. Positive and negative charges. All we do is separate them by some means and thus make available what we call a difference of potential, whereupon if we connect the points where the charges are gathered, we have a flow of charge, which we call an electric current. Now the question is, how do we produce an electric current? Let's go to some absolutely primitive things. Here I have a lemon. So somebody says, now, what are you going to do with a lemon, Professor? I'm going to make an electric circuit, produce electric current. I have here a sliver of zinc. I'm going to stick it into the lemon. I have here a sliver of copper. I'm going to stick it into the lemon. Notice the requirement. 2 different metals and an electrolyte. A solution which makes available some stuff for electric migration. Here is a meter, a very sensitive galvanometer, a galvanic meter. Its purpose is merely to detect the existence of an electric current, not really to make any measurements as to how much it is. I'm going to connect this meter to the zinc electrode and another terminal of the meter to the copper electrode. Now watch that meter. Watch it. Oh-ho! There you are. Now I'm going to exchange the polarity. Watch it now. Direction the other way. So, this that I have here, an acid solution and 2 different metals, we call a voltaic, V-O-L-T-A-I-C, a voltaic cell named after that wonderful Italian Alessandro Volta of Como, Italy, who is commemorated indeed in Como with a temple to Alessandro Volta. Now, I say, 2 different metals and an electrolyte. Observe the following. The saliva in my mouth is an electrolyte. I have here 2 different metals. I'm going to put these 2 metals in my mouth. Watch the meter. Watch it very closely. Watch. Watch. Got to see the meter. Aha. There was a motion of the needle. So you see, the acid solution in my mouth is the electrolyte and 2 different metals. Question. Can I get an electromotive force, a difference of potential from a grapefruit? Yes. Can I get it from an orange? Yes. Can I get it from an apple? I won't answer that. And how about getting it from a potato? So what constitutes a voltaic cell? Answer. 2 different metals. Here I have copper and carbon. Here I have carbon and lead, as long as I have 2 different metals. Now, supposing I have 2 identical metals, lead and lead, in an acidic solution, in an electrolyte, will I get anything? Answer, no. So the question arises, all the plates in your storage battery are lead plates. How then come we get any electrical energy from a system which is all 1 metal? Answer, it is not all 1 metal, because when the battery is charged, some plates become different from other plates, and thus we provide 2 different kinds of plates. Voltaic cell produces electricity. How else? Wonderful thing. Let me take 2 different kinds of wires, any 2 kinds of wires. Whoop, I'm tangled up here. Here is a wire, there's a wire. Let this be copper wire and this iron wire. Let me make the ends in 1 junction, and let me connect the other ends to a galvanometer, such as we had already. Let me make this junction at 1 temperature and this one at another temperature. What do we have? A thermocouple, and it produces electric energy. It gives rise to a difference of potential. Proof. Here I have 2 different wires connected to a 0 centimeter, and here is one of their junctions, and I'm going to warm this junction. I heat it with a match. Watch the needle. Watch it. Do I have to turn that to the... Watch it. There it is. A thermal EMF, an electromotive force due to a difference in temperature of the junctions of the thermocouple. Consider a dry cell with which you're all familiar. Dry cell. I want to write that word on the board. Dry cell. Whoop, whoop, little disaster. Dry cell. I put the dry in quotation marks. Why? The cell is not dry. It has some pasty stuff in it, manganese dioxide and other, which makes it a wet cell, but it's always sealed up tightly on top so as to keep it from oozing out. Now, what constitutes a dry cell? Answer. The central pole is carbon, the positive pole, and the can which holds it all together is zinc, and thus do we not have a voltaic cell made up of two different metals. How else can I produce an electric current? Well, here is something which is absolutely enchanting. In 1831, Michael Faraday, my beloved Faraday, whose grave I visited 2 years ago in London, Michael Faraday discovered the following. Let me have a coil of wire, and let me connect it to a sensitive detecting instrument called a galvanometer. Notice that name, galvanometer, named after Luigi Galvani, who was, in fact, a contestant with Alessandro Volta regarding the nature of electricity. So I have a coil of wire. Let me take a bar magnet, whose polarity is so. Let me thrust it into the coil. Ho-ho! We see the needle move. Let the magnet be at rest. Needle returns to zero. Let me pull it out. Needle deflects the other way. I have an alternating generator. Watch it. Here is a coil of wire, whose ends I have connected to this meter. Here is a bar magnet. Watch the meter. We should see all the system. Notice when the magnet is at rest, there is no change of magnetic flux, and therefore no current arising, no difference of potential. Now let me double the magnets. I doubled them. But if you noticed how they went together, it is obvious that the north pole of one has annulled the south pole of the other, and if they are of equal pole strength, we should get nothing. Watch it. Very feeble. Very feeble. Now let me put them like pole to like pole. Notice they are repelling each other. I'm going to squeeze them together. Now we should get an additive effect. Watch it. Notice it requires motion or change of magnetic flux threading the coil. Or let me take a real strong magnet and use this as a bar magnet. Watch it now. Ho-ho! Notice, no motion, no EMF. Let me move out of the way of that camera. So there I have an alternating generator. Instead, then, of moving a bar magnet in a coil, supposing I had a coil of wire wound on a frame, and I had a handle, and I could turn the coil, and I could encircle that coil with a magnetic field. I would have a magnetoelectric generator. I have one here. There is a coil inside here, which I can turn with a crank. And you notice I get enough difference of potential arising to excite, light, energize an ordinary incandescent house lamp. There it is. Now, I am going to increase the magnetic field that envelops that coil. Here I have a strong Alnico magnet. I'm going to couple the fields. Watch now. Watch the lamp. Ho-ho! The lamp does not light at all. What have I done? Obviously, I have the polarity here annulling the polarity there so that the field is nearly zero. Let me turn this one around. That way. And now watch. Aha! The lamp is brighter. Now, that current that I have generated there is an alternating one. Proof. Here is a two-pole lamp. A lamp which fires first on one side and then on the other. Watch it. How many see two things, three things, four things not right? One, the lamp has too high a resistance. Maybe the field isn't strong enough. Or maybe I don't turn fast enough. Oh, there's a little flicker. I'm going to fix it. I'm going to fix it. There we are. There we are. And you notice the alternations, which make clear that it is an alternating current generator. Right? Question. Very exciting question for students to contemplate. Supposing I had a vessel, glass, in which I put two different electrodes, say zinc and copper, and I connect them to a galvanometer, and I have an electric current, as we witnessed on this arrangement here with the lemon and the two electrodes. Supposing I had these slabs as big as a barn door, and this vat here as big as the cellar of the Empire State Building. Would I have any greater difference of potential or greater EMF? Answer, no. The two different metals in the electrolyte, which is the same for all our adventures, gives us the same EMF, which suggests the following. Supposing I took one little drop of that electrolyte, one little drop, and I put two little slivers, one zinc and one copper, in that one drop of electrolyte, I would have the same difference of potential there as there. So somebody says, well, why do batteries have to be as big as they are? Answer, longer life-producing energy, or energy-producing life, whichever you want to get at, however you want to get at it. So, of all the means of producing electrical energy, making available electrical energy, chemical is the principal one, but more used throughout the world is this electromagnetic induction of Michael Faraday, which we call magnetoelectric generation. And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And as on every program, on every lesson, some very special business, properties and effects of electric currents. The effects are staggering in their meaning for humankind. Consider the following. I have here a heavy conductor, and just below it, a compass needle, and I'm going to align them both so that the needle is in the plane of the wire frame. Now I am going to give rise to a current in that horizontal wire by connecting to a storage battery. I'll connect first this terminal, and then momentarily to the other. And you will observe a marvelous thing, that when there is a current in this conductor, a magnetic field arises, and magnetic fields interact with magnetic fields, so we would hope the needle suffers a deflection. Watch it now, watch. There it is. And the deflection was such as to make this end of the needle come toward me. Watch it again. There it is. If now I should change the direction of the electric current by changing the polarity of my connections here, watch it now, watch it. This end of the needle should move away from me. Watch. I'm having a little trouble. Notice a little trouble to make the connection. There it is. And so we have discovered the magnetic effects of electric currents, first observed in 1820 by the Dane whose name was Ørsted, O-E-R-S-T-E-D, Hans Christian Ørsted, 1820, accidentally observed the deflection of a magnetic needle, a compass needle, in the region of a current-bearing conductor. Now that is historic, because when Michael Faraday heard that Ørsted had observed the magnetic properties of an electric current, namely that electricity produces magnetism, Faraday wrote in his notebook, "Make magnetism produce electricity." See the converse of it. And it was 11 years, 1831, before Faraday accomplished it. As he wrote to a friend, "I have been fishing lately, and it may be only a weed that I pull up. But the weed, which came to be called electromagnetic induction, has lighted the world." Indeed, when he discovered it, he showed it to the Prime Minister. And what did the Prime Minister say? "Mr. Faraday, of what use is this?" Whereupon Faraday answered it in a classical way. Let's see, yes. "Mr. Minister, one day you may be able to tax it." Wonderful commentary. So, electric currents produce magnetic fields. Another wonderful effect of an electric current. I have here two lead plates connected to a framework, and here in this vessel, some copper sulfate. I'm going to put the two lead plates, which for all purposes here look alike, in here, and connect the lead plates to a source of electric energy, a storage battery. And what will happen? The copper sulfate is an electrolyte, a good conductor, because there are ions available. I'm having trouble here. That's okay. And we should discover some dissociation of the copper sulfate, and I hope to show you that copper will be deposited on one of the plates. So I am copper plating. Here we have the conduction of electrolytes, an effect of electric currents. Here's another one, the heating effect of electric currents. I have here a framework. I want to be sure that I am not connected yet. Yes, there's the plug. Here is a framework, two pointed shafts on which I have lodged a frankfurter. So, just like that, the pointed shafts emerge here. I have the two metal rods connected to an electric lead, which I can now energize from the house line. And I say that this frankfurter will be cooked. Why? Because the meat and the stuff, the salt in solution in the meat product, is a good electrolyte and hence a good electrical conductor. And if we watch closely at the electrodes, we will see some oozing, some steam, some heat generated. Watch it now. I'll just let that go, and I'm going to get down there closely. Yeah, I see it. I see it. I see some cooking there. There it is, and you catch it on the monitor. So I am cooking a hot dog in this manner. Let me show you another wonderful effect of an electric current. Here is a copper wire and a dry cell. A dry cell. Now, if I short circuit this dry cell by connecting terminal to terminal, I have a heavy current in the wire. I'm going to put some iron filings down here, and you will see that the wire unconnected has no effect whatsoever on the filings. But now let me give rise to a current in this. Now watch. Do you see the filings connected there? There they are. Now, I don't want you to think that I have made a magnet out of that wire. No, no. There is a magnetic field associated with the current in the wire. Let's look at my hot dog. Oh, yes, there it is. Let's get it close again. There the juice is oozing, and pretty soon I'll eat it, which is what should be done with a hot dog, which is a hot dog. Another effect of electric currents. I have here a coil of wire. This demonstration is virtual. I do not do it for a reason which you will see in a moment. Now, what would I ordinarily have? In this lower vessel, I would have some mercury. The lower end of this coil of wire would just make contact with the surface of the mercury. I would connect this coil of wire, its upper end and its lower end, to a source of electric energy such as a battery. What would happen? We would have a current in the coil, and because each conductor or each loop bearing current gives rise to a magnetic field, there is some mutual interaction between the adjacent loops, whereupon the coil would do this. It would be pushed together because of a weakening of the field between adjacent loops. Now, when it does that, the lower end of the circuit would be broken, the current would cease, and it would fall back again, make contact again, and this is what the coil would be doing if I were to do the experiment for real. But now, why don't I do that? I don't do that for this reason. At every sparking and arcing at the mercury surface, some mercury is vaporized, and mercury vapor is very dangerous, exceedingly insidious and dangerous, and should be avoided. Let me take a look at our electroplating. Watch it. Here I am. Ho-ho, look at that. Isn't that wonderful? Look at that deposit of copper on this plate. A beautiful deposit of copper. Now there is some other stuff on the other plate, and I leave it as an exercise. What is the stuff on the other plate? Could I not have had, instead of a copper sulfate solution, could I have not had a silver solution of some sort, and a silver and a steel spoon that I want a silver plate? I could do that. I want to show you now, further, some wonderful magnetic properties of an electric current. I have here a coil of wire, of very few turns, heavy wire. Now, heavy wire, very few turns, means very low ohmic resistance. If I connect the ends of that coil to a storage battery, 6 volts, the battery highly charged, the internal resistance of the battery is very low. So I would have an enormously high current in the coil. Now the coil, when energized, behaves like a magnet because it gives rise to a magnetic field. And if I have a rod placed so, and I connect to a battery, a wonderful thing happens. And I call this my electromagnetic gun, because when I close the circuit, the projectile will be pulled in. If I open it, it will be thrust out, and I better move this in case we have some disaster. Oh, wait just a minute. I have to get out and see my hot dog. Yeah, watch it, my hot dog. I am disconnecting the electric circuit. I want to get on the hot dog now. I am disconnecting the electric circuit, and if you give me your attention, I will show you how wonderful this is. Wonderful. My electromagnetic gun. Watch it. Watch the iron rod, the iron core. Watch it. Now, what happened? I did not open the circuit. Therefore, the rod did not emerge, but was pulled back for a reason you'll have to explore. Now I'm going to open the circuit at a critical moment. Watch it now. Uh-oh. Oh, notice, that gun backfired. I opened the circuit at the wrong time. I'll try it now. There we are. I'm going to do it again. Oh, do you see? It's very critical. Oh, there, it backfired, which means this is a very dangerous gun. It can shoot the shooter. I'll try it once more. Ah, there we are. And would you believe it? I have made such a gun which can shoot such an iron bar about 30 feet. Now, if you pointed that, do you see you could have a silent weapon? Shot silently, travel silently. More on the heating effect of an electric current. I have here a length of copper wire. Here a fully charged storage battery. Let me short the battery. by putting across its terminals, such a copper wire. Watch the wire. Watch it. There it is. Melted copper. I'll do it once more because this is very dramatic. Let me tell you further. It is a very unhappy thing for the storage battery, too. But then again, anything in the name of science, as you know. Watch it. There it is. The heating effect of an electric current. Now, regarding the magnetic effects of electric currents, astonishing. Here is a heavy metal bar, and here another heavy metal bar. And what could I show with this? Let me give rise to a current in this bar, and let me give rise to a current in that bar. Depending upon the direction of the currents, either the same way or in opposite directions, the bars would either be pushed apart or pushed together. And this is very significant for transmission lines, because, as you know, if we have two transmission cables that are too close upon each other, the mutual interaction due to the magnetic fields is likely to bring them together and short them out. So we must have regard for those matters. Are you not agreed that the properties of electric currents are enchanting to contemplate? And I thank you for watching. How do you do, ladies and gentlemen, and teachers and boys and girls? I am Julius Sumner Miller, and physics is my business. And today, some very special business entitled Adventures in Electromagnetism. I hope you have detected in the several programs we have presented, produced, my phrase, my word, adventures. That's what these must be, how these must be viewed. They are intellectual adventures filled with drama and good for the spirit and the soul. So what do we have? Oh, before I get on it, I had on my lecture table here, at an earlier hour, a beaker with some copper sulfate solution in it. Some hours had elapsed, and there must certainly have been some crystals already in the solution, but they were added to by the deposition of atoms, millions upon millions, giving us a crystal of this beautiful geometry and design and color. And I am always led to ask, how do the atoms know where to go? How do they know where to go in order to form the crystal of such and such a shape or geometry? But regarding electromagnetism, supposing I had an iron ring, like a donut made of iron, and I put a coil of wire around one edge of it, and another coil around the other. And this is exactly what Michael Faraday did with an anchor ring, that is a link of chain from an anchor chain. And what did he do? He gave rise, by connecting to some seat of electrical energy, he gave rise to a current in this coil. On this side, he had a detecting instrument, which I will call a galvanometer. And a strange and wonderful thing happened. When he closed the circuit on this wire, on this coil, the needle showed a deflection over there, and no physical connection between this coil and that one. And this was the beginning of the transformer. I have such a thing as Faraday might have used. Here is an iron ring like a donut, and there is a coil of wire, and there is another coil of wire, and they are not connected with each other. This one I have connected its ends to a detection instrument, a galvanometer. And by the way, I'm reminded to tell you, Faraday needed some insulated wire. And how do you suppose he got the insulation? He tore off strips from his wife's petticoats and wrapped the wire and thus insulated it. Isn't that enchanting to think about? Now, I am going to connect the one coil to the ends of the terminals of this battery. And watch what happens when I do that. Watch the needle now. Whoa! So, on the make, we have a deflection in one direction. When the circuit is kept closed, the current is steady, but it is a change of current which gives rise to a changing magnetic field, which gives rise to induction felt by the other coil. If this is the one I energize, we usually call this the primary, and this is the secondary. But I could turn them around and interchange their names. A little more of the same, which is very exciting. Here is a coil of wire of so many turns. Here is another coil of wire of so many turns. I am going to put this coil inside of that one, and the degree to which they are coalesced, let us say, we call the coupling. Now, I am going to connect the outer coil to this meter, and then I am going to connect the inner coil momentarily to the battery. And you watch the needle. Watch it now. I'll come over this way. Watch. The deflection is feeble. The coupling is very poor. The induction is not so good. Let me increase the coupling by having the inner one more inside the outer one. Now watch. Oh, I'm having a little trouble there. A little more deflection. Let me couple them completely. A little more deflection. Now you will observe that these are air cores. That is, the central place in here is empty of any magnetic stuff. So what am I going to do? I am going to put an iron rod, which is a big, heavy 80-penny nail. I am going to put that inside the inner coil. Now I'm going to connect the circuit momentarily. Watch it now. Watch. Oh, look at that. So you see why it is that a transformer, which may be viewed as one coil and another coil, has best or works best with an iron core. Electromagnetic induction. And to whom are we indebted for this? Michael Faraday. Now, consider this enchanting business. Here is a coil of wire of so many turns, wound in a certain direction. I have the coil connected to a zero-centered meter. Here is the pole of a magnet. Watch it. Deflection to the left, deflection to the right, deflection to the left, deflection to the right. Now I'm going to connect to the other coil. Deflection to the right, deflection to the left, twice as much. Answer, twice as many turns on this coil as on this one. If now I put one pole of a magnet in this one and one pole of a magnet, the other pole of the magnet in that one, we find an interesting thing. Watch it. You see that the EMFs, the electromotive forces, add. Now let me go to another coil, this one. Watch it. Whoop. 3 or so to my, your left. 4 probably. Let me turn around the magnet. Now let me go to the next coil. Watch it. Turn the magnet around. Now let me see how the EMFs behave when put together jointly. Watch it. This suggests what? This coil has the same number of turns as this one, and they are wound in opposite directions, so the insertion of the North Pole here gives rise to an EMF with a current in a certain direction, and this one annuls it. So the effect is zero, practically. Now let me go to the two last ones. Watch it. 3, 3. Change the magnet. 3, 3. Now let me go to the outermost coil. 3, 3. 3, 3. Now let me see how the EMFs add. Watch it. If the scale were big enough, it would go to 6. So this suggests at once how these coils are wound. Now consider the following. Supposing I had a bar of magnetic stuff like iron, and I wrapped a few turns of heavy wire around it, and I connected this to some difference of potential like a storage battery, I would have a current in that winding. That current in the winding gives rise to a magnetic field. Supposing now I had another winding insulated from the first, which I shall call the primary, and this secondary winding of many, many thousands of turns of fine wire. The current in the primary heavy winding would give rise to induction in the secondary winding, and if I had the secondary terminals separated in some such manner, I would have an enormous difference of potential. I'm going to show you how high it could be. Here I have a 6-volt battery. 6 volts between here and there. Here I have such an induction coil. I am connecting the battery to the primary of this coil, and the secondary is shown by this gap here between the two terminals. Watch it. Now somebody says, what's the potential difference there, Professor? I would say it's 40 or 50,000 volts. 40 or 50,000. Yeah. Now that's pretty heavy stuff. Well, let's look at this one. Here in this box, I have such a bar, which is laminated in order to reduce hysteresis effects, minimize the heating. There is a heavy coil of wire around the primary, which I energize with the storage battery. Here are the terminals of the secondary, right there. And with this instrument, what can I get? Well, watch it. I'm going to connect this one there. There we are. Look at here. Oh, mamma mia. In dry air, the difference of potential is about 30,000 volts per centimeter. And remember, there are 2.5 centimeters in an inch. So I have a couple 100,000 volts there. And you see a wonderful thing taking place, some sparking. And as I like to ask my students and colleagues, what is it that we see when we see a spark? And what do we hear when we hear the sound? And why is the light that we see high in the blue? What I'm getting at, people, boys and girls and teachers, is this, that when we witness a phenomenon so quickly disposed of as I have disposed of this, there must arise many, many questions of a penetrating sort. So I'll say again, why do we hear some sound? Why is the light blue? Further than that, I detect, I smell something. So you see what my senses are revealing to me. My auditory sense revealing the sound, the optical sense revealing the light, and my olfactory sense revealing some odor. As a matter of fact, it's very pleasant. What is it? Ozone. Ozone is being produced. Ozone is being produced by that electric discharge in air. And that has enormous consequence for the human race. Because when we have a lightning storm and there is great sparking between clouds and earth, ozone is produced in abundance, and this has some virtue for humankind. So we have explored, in a passing and rather superficial way, these things which I call adventures in electromagnetism. And I thank you for watching. How do you do, ladies and gentlemen, teachers, boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come once more to what I have entitled Further Adventures in Electromagnetism. The subject is filled with drama, quite stirring to contemplate. Consider the following. Here is a horseshoe magnet, very, very strong. Indeed, strange properties. It is called an alnico magnet. And imagine this: nickel, highly magnetic; cobalt, highly magnetic; aluminum, or for the Britishers and the Australians, aluminium, very feebly magnetic, if indeed at all. And yet, when put together in proper parts, gives us a fantastically strong magnet. So here is an alnico magnet. I'm going to show you how strong it is. There is a keeper, a bar to put across its terminals. Watch. Oh, it's a very strong magnet. Now, I am going to put a wire, a limp, feeble wire, in between the poles. Very loose wire. And I'm going to give rise to a current in this wire by connecting to a storage battery. Watch the wire. Watch it. Oh, it jumped. It jumped. There it is. I want to do it again. There it is. Why? Well, the current-bearing conductor gave rise to a magnetic field which interacted with the magnetic field there, and the forces were enormously stout. Consider this more enchanting. I have a typewriter roller. You know, the roller on your typewriter. And I have wound it with some turns of wire. And the ends of this winding I'm going to connect to 110 volts AC in this room, like in your home. This means that the coil is energized with an alternating current, which grows and decays and grows and decays. Therefore, we have a change in the magnetic flux, and therefore a changing magnetic field here around this coil. I'm going to show you what it can do. Here is a little coil of wire, few turns, to the ends of which I have an automobile headlamp fixed. I am going to close the circuit, energize this coil, and bring this lamp down. Watch it. Fantastic. No physical connections whatsoever. None whatsoever. Only electromagnetic. Consider this. A copper ring, solid, heavy, large cross-section, small ohmic resistance. I'm going to rest this ring on my hand, so close the circuit. The current in this primary coil gives rise by induction to a current in this, and they both give rise to magnetic fields which are repulsive in nature. Watch this now. Watch it. There it is. It jumped up. Indeed, let me take two of them. Two of them are certainly heavier than one. Watch it. we'll see an astonishing thing. The jump is even higher. There it is. And if indeed I took a whole string of them, 5 or 6, you see they constitute a single conductor of larger cross-section and hence of smaller ohmic resistance. Watch this now. Watch this. This is terrific. There it is. Now, here I have a coil of wire, protected a little with adhesive tape. I'm going to put this coil of wire near this coil, but no physical connections there. And this secondary coil is connected to an ordinary, what is that, a 40-watt lamp or some such. I'm going to energize the primary. Let's see what happens to the lamp. Very feebly lighted, very feebly. Why? Well, this is an air core. Very low permeability. The induction is very low. So what am I going to do? I am going to put an iron rod in the core of this secondary and watch the lamp. Now, watch it. Watch it. Somebody says, what's that hum? Well, 60-cycle hum, about which I won't say anything here. But do you notice how strong, how much the induction is aided, enhanced, abetted, favored by making this core highly permeable with soft iron? Here's something that I could do. We'll imagine this as a virtual experiment. Here is a hollow tube. Oh, wait a minute, hollow tube. I think that language is redundant. Just a tube would be good enough. Copper, closed, with a little side arm and a tiny, tiny hole. What would I do? I would fill this tube with water. I would then hold it with a pair of pliers, bring it down over the induction coil, and nearly instantly, the water in here boils. Why? Well, the induction heating is phenomenally rapid, and the water is brought to a boil, and I have a question. There is only one entrance to this tube, one tiny little hole. Question, how can I get the water into that tube? How? That's a good one for you to contemplate. So then, for electromagnetic induction and the business of my jumping rings. But before I finish, the hole in this typewriter roller I have filled with strands of baling wire from bales of hay, very soft iron wire. I say that when I energize this coil, this becomes an electromagnet. Proof. I have here an iron bar. I'm going to hold that about an inch above, close the circuit. Watch. Watch. Gonna hold it. Notice I can't hold it. 2 men couldn't hold it. Why? Very strongly magnetized. Let's look further. Electromagnetic induction. This one is filled with drama, enchantment. Here is an aluminum disc. Aluminum. Remember my commentary. Aluminum is not magnetic. Correction. It is magnetic because all stuff is magnetic to more or less degree, but it is highly, highly non-magnetic, or feebly magnetic. I'll show you that it is feebly magnetic. There ain't no stuff there. Now I'm going to mount this disc on a vertical pin so it can spin on a vertical axis horizontally. But I'm going to put it at rest. Here I'm going to take the magnet hanging on a piece of clothesline, and I'm going to twist up the magnet so, storing some twist energy, as I am given to say, in this string, so that the magnet now unwinds of its own accord. Now I'm going to hold this centrally over that disc, which is at rest, and you will witness an extraordinary thing. Watch it. Watch it. That disc is turning. That disc is turning. Now somebody says, Professor, that disc is turning because of the viscous friction of the air. It drags it along. No, 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 no. No dragging along. Here's what's happening. The rotating magnet gives rise to induction in the plate. In the plate, there arises an electric current. The electric current in the plate gives rise to a magnetic field, which interacts with this magnetic field. And this that I have shown you is the classical demonstration done by Jean-Dominique Francois Arago, A-R-A-G-O, a wonderful Frenchman, and so we call it Arago's disc. Regarding Arago, he made a commentary concerning Gauss, the great German mathematician. What did he say of Gauss? Carl Friedrich Gauss. Gauss. He calculates with the ease as eagles do fly. He calculates with the ease as eagles do fly. That was Gauss. So, electromagnetic induction. Here is another one of like complexion. Here is an aluminum disc, and as you would expect, if I showed this in Australia or the UK, I'd have to say aluminium. Here is an aluminium disc. It's mounted on a vertical shaft, and it's free to spin horizontally. I'm going to spin it, and we'll get a feeling for its spin life. How long is it going to spin? Watch it. Quite some time. Now, here is a strong magnet, powerful magnet. I'm going to advance the magnet so as to embrace the disc in the magnetic field. Here we have a moving conductor in a magnetic field. A current is induced in the conductor. That current gives rise to a magnetic field which interferes or interacts with the magnetic field here. Watch it. Watch it now. A magnetic break. And the principle that we have here invoked of the disk being brought to rest by the interaction of magnetic fields is known as Lenz's law, L-E-N-Z, a Russian who gave us this matter. So, mark you, on occasion I have taken a moment to name the men associated with our affairs. And in nearly every instance, I have tried to point out the national origin. Michael Faraday, an Englishman. Gauss, a German. Lenz, a Russian. Who else? Isaac Newton, an Englishman. Einstein, a Jew. And so, Ohm, a German. Ørsted, a Dane. What I'm trying to say is, it is very essential to pay proper tribute to the national origin of these men, for no single peoples have any special claim to intellectual competence. A magnetic break. Talking about magnetism, let's go back to an old-fashioned matter. Here is one of those strong Alnico magnets, and I'm going to toss some nails into the field associated with these two poles. Watch it. Watch it. Look at that. Look at that. And the reason I do this is to point out the following. Let us look at a horseshoe magnet. Here is a horseshoe magnet. If this is of north polarity and this of south polarity, the field across here is very, very strong. And I am reminded of an experiment that Michael Faraday did for the children in the Royal Society. What did he do? He threw some iron filings at random, and it made such an arch, and he described it as a little tunnel through which a little mouse could go. You see the humanism that filled Michael Faraday's spirit. He thought of a little mouse going through this little tunnel. And so, where are we? Electromagnetic phenomena, first observed by Ørsted in 1820, when he discovered that a current-bearing conductor gives rise to a magnetic field, and then 11 years later, advanced so profoundly by Michael Faraday with his discovery of electromagnetic induction, which, I always say, lighted the world. And I thank you for listening. How do you do, ladies and gentlemen, and teachers, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come to another program on electricity, magnetism, and such allied subjects, which I have entitled Miscellaneous and Wondrous Things. Again, I emphasize the spirit that the language is intended to convey. Wondrous things, for indeed they are to contemplate. Consider the following. I have here two clear glass, incandescent, carbon filament, 110 volt lamps. That covers the description, I guess. I'm going to energize one of them. Now, I'm not going to tell you whether I'm going to energize it with alternating current or direct current, but I'm going to energize it. There it is. There is a flow of charge in the wire. The wire offers some resistance, gets hot, and emits light. Question, is that lamp energized with alternating current or with direct current? We shall investigate it. If the current in that filament is alternating, it first surges this away and then that away, 120 times per second on 60 cycles. It gives rise to a magnetic field, which is oscillating, changing. Accordingly, if I present an alien magnetic field to that wire loop, to that filament, there should be some interaction between magnetic fields. And we shall tell in a minute. Here is a horseshoe magnet. Watch the filament. Notice that very rapid oscillation. Clearly, that lamp is energized with alternating current. I leave it as an exercise for you to think about. Supposing I energize this other identical lamp, or indeed this first one, with direct current of the same voltage. The lamps would be identically bright, pretty nearly, which is a technical matter. And I ask, supposing I presented an external magnetic field to that DC energized filament, what would the filaments do? That's a very good exercise. Very good. Consider another very dramatic. Here I have a solenoid. A solenoid is a loop endlessly of wire fixed to a lucite plate. I am going to give rise to a current in that solenoid, in the wire. And a wonderful thing takes place. Here I will show you the solenoid. And let me energize it by impressing a difference of potential, as we say, 6 volts. A current is in this wire, and a wonderful thing is to be seen. That solenoid behaves as if it were a bar magnet. I'm going to show you that. I'm going to sprinkle some iron filings here at random. Sprinkle some iron filings at random. They have taken up a chaotic position. Chaotic. Now I am going to connect that coil to a battery and minimize friction a little bit by such action, and watch the beautiful pattern taken up by the filings. Watch it. There it is, beautiful, just like a magnetic field. And I call your attention to this very important thing. Very near the wire, the magnetic field is very strong, and so the filings are bundled up in little bundles. Let me just disturb that and put it in chaos again and show it to you once again. Watch the instantaneity with which the field takes hold of the iron filings and aligns them. Watch this now. Look at that. Incredible. Incredibly fast. Next demonstration. A very wonderful problem. Indeed, one which is not so easily answered. I have here 2 incandescent lamps. Here is one, and there is another, and I am going to connect them to 110 volts, 60 cycle, alternating current. And they are in series. Here is the filament, and here is the filament. One of them, the small one, is an 11-volt lamp. Somebody says, oh, I've never heard of an 11-volt lamp. Well, when you deal with me and physics, you're likely to hear of very strange things. An 11-volt lamp. And this, 11 watts, 11 watts, excuse me, 11 watts, 11 watts, sorry. And this one is a 100-watt lamp, 100-watt lamp. Now, they are in series. I connect them to the house line. Question, what will we see? What will we see? Will this one light up, as we say? Will that one light up? Or will they both light up? Now, you know my philosophy. I am not so ready with answers because I don't think answers are so important. What is important is that you think it out logically and rationally and come to a proper understanding. Because, as you have heard me say, it is not so good how much you know. It is most important how much you understand. So, I'm going to reveal to you what happens. Watch. I'm going to connect them. I'm going to connect them. Pretty soon, I'll connect them. Watch. Aha. The lower wattage lamp is energized and reveals some light. I want to know, why is it so? Indeed, this is a wonderful expression for you to carry with you all your life, asking, why is it so? That's a wonderful question. I have spent 60 years with that phrase, asking constantly, why is it so? Consider now the following. Here is a mechanism called a horn gap. Notice, shaped like a megaphone, like a horn, sometimes called Jacob's ladder. I have the ends of this connected to that high voltage induction coil. I'm going to give rise to a discharge at the nearest separation of the gap. Watch it now. Watch. I am energizing the induction coil with a 6-volt battery, giving me 150,000 volts across here or so. Watch. Whoop, I got a little, well, some strange things happen when you deal with electricity. Question. The discharge takes place across this narrow gap. I had hoped to find it climb up and show evidence of discharge at 3 or 4 inches, because I can get 3 or 4 inches here. I want to know why this discharge does not climb. I'm going to tell you why. It doesn't climb because ionization is not so readily accomplished in this region, and we need ions for electric energy transfer. Question, how could I get the discharge to climb the gap? Answer, by lighting a candle below or holding a match below, and the heat of the match or the candle would give rise to further ions which would aid the climb of the discharge. Now you say, well, why don't you do it, Professor? The answer is there is too much convection in this room, the hot air that I'm blowing, some would say, whereupon there is not the confinement of the heat energy that I want for convection. Now, one more enchanting question. I have here a cubical frame which I will represent on the board like this. There it is. And each edge of this cube has a resistance fixed to it. A resistance. A resistance. I won't draw the rest. Resistance, R, 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 R. Every side, correction, every edge of this cube has a resistance R. The problem is classic in this business. Supposing I consider this point A and a remote diagonal B. That is, these are the points, this one and this one. Question, what is the total ohmic resistance between this point and this point of this cubical structure of resistors? The total resistance between A and B. I'm going to give you the answer. The answer is that if R is the resistance at each place, then the total resistance between the extremities of the cubical diagonal turns out to be 5/6 of R. That is, if R is 1 ohm, then the total resistance is 5/6 ohm. I leave that as an exercise for you to do, because I remember meeting this when I was about 9 years old, and it took me 6 years to learn how to do it. See, 6 years. So what am I getting at? Do not be in a hurry to answer questions. Remember, the answer isn't important. It's how you think about them that's important. And I'll give you a further hint. There is not only one way to do it, there are 2 ways to do it. Indeed, there are 3 ways to do it. So you see how charitable I am. There are 3 possible solutions to the problem. Let's go further. Electromagnetic induction. Here I have a very strong Alnico magnet, and the gap between the poles is very tiny. You see a very tiny gap. Here I have an aluminum slab. Aluminum, remember, is not magnetic. Oh, correction, slightly magnetic. Now I'm going to drop this here in free space, as we say, and watch the rate at which it falls. Well, it falls like a freely falling body. Watch it. Incidentally, where did the sound come from? Answer, a vibrating system. So it fell under free fall. Now I'm going to let it fall in that gap. Watch it now. Watch it. I'm going to do it again. Notice how sluggishly it falls. Why? This is a conductor. It is moving in a magnetic field. The motion of a conductor in a magnetic field gives rise to a difference of potential. A difference of potential gives rise to a current. The current in the slab gives rise to a magnetic field, and magnetic fields interact with magnetic fields. Watch it. And that's Lenz's law again. Supposing I did this now, this was a solid slab. Supposing I did it with a slab that is slotted. I hope you see the slots, or slits, or whatever you wish to call them. I will show you that it will fall now much more fast, much more rapidly. There it is. And so we are coming to the close of another series of lessons, this last one on electricity and magnetism. A massively enchanting field for your exploration. And remember, whenever we think of anything, regard highly the national origin of the men whose industry and intellectual competence gave it to us forevermore. And I thank you for watching.